Hi everyone, welcome to video 3 of multiple linear regression. Let's briefly review what we went over in video 2. So first, what did the bivariate correlation table tell us about the relationships between math anxiety, stats anxiety, and confidence? So here we go. Here's our correlation table that we looked at in the last video. And as we saw, all variables are strongly correlated with each other. Our independent variables here, stats anxiety and math anxiety, they are both strongly correlated with our DV confidence. And then our independent variables are also strongly correlated with each other. So all these correlations are 0.4 or above, so all of them are strongly correlated with each other. So this is a perfect situation to do multiple regression to assess what the unique contributions are for stats anxiety in predicting confidence and math anxiety in predicting confidence, right? We have a statistical cage match here. And so what data checks do we need to do before we look at the main regression output? So first, and I should have really changed this in the last video. First, we need to check Cook's D, right? So just like for ANOVA, we need to check Cook's D values first, and then we can do the other data check. So we want to make sure that there are no potential outliers, and then we can check for normality and the new assumption, the new data check that we hadn't mentioned before, homoscedasticity, right? So homoscedasticity is like the equality of variance assumption for multiple regression, right? So remember that there's always going to be some level of error in predicting the DV from the two independent variables that we have here, right? So stats anxiety, math anxiety are the IVs, confidence is our DV, right? And we don't see any perfect correlations here. Right, so we're not going to explain 100% of the variability in our outcome. We're not going to have perfect relationships, perfect prediction here, right? So the regression analysis using the IVs is going to predict each participant's score, right? But that prediction is going to be a little off since we don't have perfect relationships here. So for every participant, there's going to be a difference between the predicted score and their actual score. Right, and that difference is called residual. And when you do a multiple regression, you can get these residuals for every participant. You'll get a new variable in SPSS, and then you create a histogram for those residuals, and you want those residuals to look like a normal distribution. You want to approximate a normal distribution. So that's homoscedasticity. All right, so that's what we went over in the last video. So let's take a look at the main regression output here, right? So this is the first table that you want to look at. It's called the model summary table, right? And so let's, we're not gonna look at every single number value in here. We're going to look at some of them. Right. But we'll first mention, right, that SPSS is helpful here in that it lists the predictors and the dependent variable here in the model summary. So here, predictors, you can see math anxiety, stats anxiety, and then you can see also the DV here is confidence, right? So that's helpful from SPSS. Right. So let's first take a look at the R value here. And you'll notice that we no longer have a lowercase r, we have a uppercase R, right? Lowercase r, lowercase italicized r, represents the bivariate relationship, that is the relationship between two continuous variables. Now we have a uppercase capital R, so this is the multiple correlation value, meaning how much do both of the independent variables correlate with the DV. So once we get a capital uppercase R, we're no longer looking at a bivariate relationship. We're looking at what we call a multivariate relationship that is more than two variables at a time. So this is how much do both of the independent variables correlate with the DV. And then right next to it, you will see R square. So this is just the R value and square it. So if you take 0.51, you square it, you will get 0.261. And the R square here is the explained variability from both of the independent variables. So just like when we were doing bivariate correlation, we had the lowercase r, we squared that lowercase r, and that gave us the shared overlap, or we could say if we multiplied that by 100, it would tell us how much the independent variable explained in the dV. So how much, percentage-wise, how much did the independent variable explain the differences or variability in our outcome here, right? Now we have a capital R squared. So this is how much both independent variables, here math anxiety, stats anxiety, how much do they both in combination, right, predict our outcome here. And you remember, this is not the first time that we've seen R squared before. If you remember from the two-way ANOVA, you remember me talking about R squared, because in the two-way ANOVA, R squared represented the total contribution of all the independent variables in predicting the dV. And that's exactly what we have here. Except in the two-way ANOVA, we were dealing with, two categorical independent variables. Here, we have two continuous independent variables, but R squared works the exact same way. How much do both of the independent variables, how well do both independent variables predict the dV? What's the total contribution of both independent variables here? And so we can take this R squared value, we can multiply it by 100 to get that percentage, right? So we can say that both independent variables explain 26.1% of the variability or differences in our outcome. That is, math anxiety and stats anxiety explain 26.1% of the differences or variability in confidence. Now, in evaluating how the magnitude, how small, let me get my words here. Just like we had guidelines for interpreting lowercase r, we can apply those same guidelines here in evaluating capital uppercase R, right? So we can say that the percentage explained here was small, medium, or large. But generally here, people usually report the R squared versus R. So when we eventually get to the write-up here in a second, you'll see that we will report R squared. But we'll use the same guidelines that we used for lowercase r in evaluating uppercase R. Right. So if our R value is anywhere from is below 0.2, then that would be a small or weak R. Anything from 0.2 to 0.39, that would be a medium, moderate R, and then anything 0.4 or above, that would be a large R, a strong R. Okay, next we have we return to F's. We have an F value here. So the F change here is the F value for the model. And you notice that we get an F value, we get 2 degrees of freedom, and so we have degrees of freedom between and degrees of freedom within, and then we also get a P value. All right, and so this F test here, this F test is assessing the significance of this F and sig value here, is testing the significance of the overall model, right? Is testing the significance of the overall model, the total model here. That is, does any independent variable significantly predict the dV? All right, so does any independent variable significantly predict the dV? And this may sort of sound similar to like when we did ANOVA, right, where we had sort of a main effect analysis, right, and that main effect told us whether there were significant differences between any of the mean scores, and then we looked at the post hoc table to see where those differences are. So that's sort of what's going on here, in that we're getting a sig value for the overall model, and then if our f value is significant here, if the p-value is significant, that means there's at least one independent variable that significantly predicts the dv here. And so our f is 23.78, degrees of freedom between 2, degrees of freedom within 135. And then our p-value here, we get the triple zeros, so we can denote that as p less than 0.001. All right, so we do have a significant p-value here. Our f value is significant. So then we can move on and check the coefficients table in the next slide. And that coefficients table will tell us which independent variables uniquely, significantly predicted our outcome here. Right. And so our p-value is significant, so that means at least one of these independent variables, math anxiety or stats anxiety, significantly, uniquely predict our outcome here. And this getting a significant model here, a significant p-value here, is not surprising. We already, when we did the bivariate, when we talked about bivariate correlation, we already know that math anxiety, right, significantly predicts confidence, right? And we know from the bivariate correlations that we just looked at here, we know that math anxiety and stats anxiety both strongly correlate with the DV, right? So at least one of these independent variables, maybe both, uniquely predict our outcome here, confidence. So getting a significant p-value is not that surprising here. So we know that both of the independent variables explain 26.1% of the variability in our outcome. We know that at least one of them uniquely predicts our outcome here. So we don't know if both do or if one is going to win out. We need to find out which independent variables predict the outcome here. We need to check the coefficients table, and that will be in the next video. But right now, we are going to start filling out the write-up for this multiple regression analysis, right? So you will find this Word doc on Canvas, and then I recommend that you download this Word doc and then complete it along with me here. So if we go to Canvas. Right. If we go to Canvas, under the correlation and regression module, you'll see regression write-up lecture example blank. And so this is the Word document that you want to download. And this will look like this. All right, so we're looking at the effects of stats anxiety and math anxiety on confidence. All right, and it says we conducted a simultaneous multiple linear regression to test the unique effects about blank and effects of anxiety about blank and anxiety about blank on blank. So we have, so in the first paragraph, just like any results section, we are telling the audience what analysis we did and why we did it, right? So we have 2 blanks and then 1 blank. So hopefully it's pretty self-explanatory here that we conducted a simultaneous multiple regression to test the unique effects of anxiety about, and then here you can either do like, doing math problems and anxiety about taking a stats class on confidence in doing well in the stats class course. And then maybe just put in parentheses, since we won't repeat this full phrase, anxiety about doing math problems, we'll just call that math anxiety, and anxiety about taking a stats course, we'll just call that stats anxiety, as we have, and then on confidence in doing well in the course, and then parentheses, confidence. So that is the first paragraph, and now we can move on to the second paragraph here, where we talk about the results for the overall regression model. And so this second paragraph here sort of feels like doing a main effect for a one-way ANOVA. So yeah, because you can see that we have the F, and then we'll have degrees of freedom between and within, and then the F value, P value, and R square value. Right, so we can take these from the output, go back here, right? So degrees of freedom between is 2, within 135. And then equals, we have our F value, actual F value, 23.78. And then our P value for the model here. So we get the triple zeros, so we denote that as P less than 0.001. And then our R square value of 0.261. And so we can say the IVs overall explained, 1% of the variability and confidence, which is A. So the R value here was 0.51. And again, we can use the same guidelines that we use for lowercase r. So 0.51 is greater than 0.4. So this would be a large percentage. That there is pretty strong relationships between the IVs and the DV here. All right, so those are the first two paragraphs, and then again to find out which independent variables uniquely, significantly predicted the outcome here, confidence, we'll have to go to the coefficients table, and that will be in the next video.